Welcome to Chapter 4. In this chapter, we're going to begin our study of integration, and in Section 4.1, we will talk about antiderivatives and indefinite integrals. We have three objectives in this lesson. We want to be able to essentially take the antiderivative of an equation, which is the general solution of a differential equation, and use the indefinite integral notation for antiderivatives. We're also going to find out some basic integration rules and find a particular solution of a differential equation. So in the past couple of chapters, our focus was really to find the derivative, which helps us to solve that tangent line problem, which was one of our initial big questions in calculus. The other big question, if you can think back that far to several weeks ago, was the area problem. We wanted to estimate the area under a curve. Well, that is where antiderivatives are going to come into play. And antiderivatives are exactly what they sound like. They're the opposite of a derivative. So what we've done so far is we've had f of x, and we've been able to take the derivative of f of x and find that that solution was f prime of x. So what we're going to start with now is I'm going to give you the derivative. We're going to integrate it, which we'll talk about in a little bit. So we're going to integrate it, and we're going to end up back where we started at f of x. So it's the opposite of finding the derivative is an antiderivative. The notation that you'll see, again, we'll talk more about notation, including the integral in a little bit, but notice here in the definition, they're using f, capital F, as the antiderivative, so they're saying that's this guy, and the original function is f of x. So they're saying if you started with f of x and you integrate f of x, you get capital f of x, which is the antiderivative. So let's look at a question together. Unfortunately, we're not at tables, so you're just going to have to think of this on your own. Suppose I asked what function has a derivative of f of x equals 3x. So think about how that's going to work. We know that when we took the derivative of something, we used the power rule. So essentially I'm saying, what would f of x be? So I knew if I used the power rule that this guy had to have decreased by 1, which means I had to have had an x squared here. Because when I take the derivative of it, I need it to end up at x to the first. So I had to increase that power by 1. Then I think, well, I need it to be 3, but I know that I'm going to be taking that 2 times whatever's out here. So what if I had this as 3 halves x? So now let's think about what would f prime of x be? Would that equal 3x? Well, if I took 2 times 3 halves, I would get 3. If I took x to 1 degree less, I would get 3x. But now my question is that the only answer? What if I had plus 7 at the end? Wouldn't I still end up at 3x? What if I had minus 22 at the end? Wouldn't I still end up at 3x? Yes. So essentially what I have is a whole family of functions, and obviously I can't have another x in the equation, but I could have anything else that I'm adding or subtracting to that function that's a constant, because when I take the derivative it will go away. So that process that we just went through and just barely touched on, and obviously we'll learn so much more about, is called finding the antiderivative of a function, or evaluating the indefinite integral of a function, or finding the general solution of a differential equation. So those are all the same thing that we're doing, and essentially we're saying let's find an antiderivative. And again, why is it an antiderivative? Because as we talked about before, when I take the antiderivative, I could have ended up with any kind of c. So that plus c is what makes it an antiderivative. If we talk about the antiderivative, that's when we talk about particular solutions. So when we talk about the general solution, that's because we're using plus c. When we talk about a particular solution, that c will be an actual value that we solve for. So essentially we're saying that we can create an entire family of antiderivatives of a function. So just like we talked about before, if I were finding the antiderivative of 2x, I know that if I had x squared and took the derivative of x squared, the derivative would be 2x. So I can add anything to that, plus 7, x squared minus 3, x squared plus 2, x squared minus 1000. Anything I want I can add or subtract to x squared, because when I take the derivative, I'm still going to end up back here at 2x. And so again, these values that I'm adding and subtracting are all in the same family, and of course would just shift our graph a little bit. And so again, the c that creates that family, so instead of having to write out all of the options, I just write plus c, and c is called the constant of integration. So just to make sure we have our notation down, we have our entire function sort of laid out for us here, and I'm just going to go through all of the parts with you. Of course, this, I don't have it labeled, but obviously that's the integral sign, which tells us that we're integrating or finding the integral. What we're finding the integral of is the integrand. And then of course we have the variable of integration, which just is the same as when I had dx, which told me I'm deriving with respect to x. So it's just telling us which variable to use. It's important that we always have that, however. Then when I find my solution, this is the antiderivative, the capital F of x, and then of course the constant of integration, which most of the time you'll just hear me call a constant. And again, this is the antiderivative, and this is an indefinite integral. So you'll find that later we talk about definite integrals. Indefinite integrals will use a c and won't have any values here. So when you start seeing values on your integral, that's when we're going to talk about definite integrals. Again, this slide is really just to make sure we understand the terminology. So it's a general antiderivative or a general solution because we're using that plus c. And this is all of a differential equation. So there's a whole lot to differential equations that obviously we're not going to, there's a whole class that you could take on differential equations. But essentially a differential equation is an equation that involves x and y and derivatives of y. So we talked a little bit about this before when we were trying to do implicit differentiation. It's essentially the same idea. So let's take a look at a few examples. And if you ever get stuck, we're going to use the power rule. And the power rule is just a way for us to essentially give us a pattern for being able to find the antiderivative. So the same way we had a power rule when we were finding the derivative of a function, we said, well, if the original function was x to the n, then the derivative was n times x to the n minus 1. So that was the power rule for derivatives. The power rule for integrals, or antiderivatives, is essentially taking that same concept, but obviously going in reverse. So we're saying if we're integrating x of n, dx just tells us we're integrating with respect to x, then we need to increase this power by 1, but we also need to have divided by that same exponent. And then of course add the plus c. So think back to when we had our first example and I said 3x, what was the original function? So when I integrated it, I said, well, there must have been a 2 here, and this must have been 3/2 in order to make that work. And we didn't worry about the plus c at that point. But again, without even knowing it, we used the power rule because we increased the power by 1, and then of course divided by whatever that power was. So let's try it. And again, if you feel comfortable, go ahead and try these 4 on your own and then press play. So the first one, y prime equals 2, meaning we've already found the derivative is 2. What was the original function? So again, I know that there's no x here, which means the original function must have had an x with the 2, and then of course plus c. So it should be 2x plus c. Again, if I took the derivative, I would end up with just a 2 here and nothing here. Next, for x, so again, if I already had an x, I had to increase by 1, so it was x to the first, I increased it, and then I took 4 divided by 2 to get the 2. The next one, this is a 2, which means I'm going to make it a 3, and then I need to divide by 3, so that gives me x cubed plus c. Then of course the last one I can't use the power rule on, I just have to know my derivatives. So I'm saying what did I start with that has a derivative of cosine of x, and hopefully you know that's sine of x plus c.